Hello, in this video we cover section 12.2 and we are going to be introducing a new function that we have never discussed before. The last section we talked about the exponential functions that have the form f of x equals b to the x. And today we're going to look at, like I said, the function new type called the logarithmic function, and they, it turns out, are very related to the exponential functions that we looked at in the last section. We'll see how that works. So just as a warm-up here, we talked last time about how to graph exponential functions, and so if I had some different xy pairs, if my power is -3, remember that's 2 to the -3 power. We know 2 to the third power is 8. So 2 to the -3 power is 1 over 8. We have 2 to the -2 power. 2 squared is 4. So 2 to the -2 is 1 over 4. And we could continue in this fashion. Next one would be 1/2. 2 to the 0 power is 1. 2 to the first power is 2. 2 squared is 4. And 2 cubed is 8. And like I said, we did this last class. So let's go ahead and put these points on our graph. So if we put our points on, we have -3, 1/8. It's going to be just above the x-axis. We have -2, 1/4. Which is just a little bit higher. That's the point, -2, 1/4. We have -1, 1/2. We have 0, 1. And we have 1, 2. We have 2, 4. And we have 3, 8. And you'll remember that the shape of exponential functions gets really close to the x-axis, never touches it. We have what's called a horizontal asymptote there, and then it quickly increases in value. We say it's something like this has exponential growth. Just a reminder here, there's this line here in red. I'll draw it. We said it was a horizontal asymptote. As a reminder, that's a line that you can get really close to but never touch, and that is the line y equals 0 in this case. Now let's ask ourselves a question. Does this particular graph pass the horizontal line test? Can you pass a horizontal line through this graph and have it cross in more than one place? And the answer to that question is no. So it does pass the horizontal line test. Which means what? What does that mean? Ask yourself that question. If it passes the horizontal line test, what does it say about the function? Well, hopefully you said it means the function is 1 to 1. Which brings up the second question. Does that function have an inverse? And the answer is yes, because the function's 1 to 1. If the function's 1 to 1, then it does have an inverse. And if you'll recall, we talked about this in the last chapter. If we wanted to go ahead and plot the inverse function, we just take these points and reverse the x and the y coordinates. Because, for example, if our function turns 3 into 8, the inverse function will turn 8 back into 3. And we can do that with all of these points. So our inverse function table, g, this is x, and we'll call this new function f of x. The inverse function would turn 1/8 back into -3. It would turn 1/4 back into -2. It would turn 1/2 back into -1. It would turn 1 back into 0, and 2 back into 1, and 4 back into 2, and 8 back into 3. And we would get all these points here. We get the point 1/8 -3, and 1/4 -2, and 1/2 -1, and 1 0, and 2 1, and 4 2, and 8 3. I draw this in another color here, in blue maybe. We can see that this blue line here would be our new function f of x, where the old graph was our g of x. And now it appears that the graph, instead of getting really close to the x-axis, we now have what we call a vertical asymptote. This is a vertical asymptote that the blue graph gets really close to but never touches. That's the equation x equals 0 in this case. And remember, we talked about that if we were to draw in a horizontal line here, we shade this. If I draw that line, the function g of x and the function f of x are reflections of each other across that yellow line. That makes them what? What do we recall? It makes them inverse functions. We see this with all graphs of functions and their inverses. So what we really need is we need a name for this function that is the inverse function of an exponential function. And this is where we get the logarithmic function from. So that f of x that we just plotted above, that was the inverse function of, remember our original function was f of x equals 2 to the x. It was an exponent with base 2. The base is 2. It will have a function f of x called the logarithmic function, and it's denoted f of x equals log, and then it looks like there's this little subscript 2 and then an x, and it reads logarithm base 2 of x, or we're going to say for short log base 2 of x. One thing I want you to notice is that both our original function 2 to the x power and also our logarithmic function have base 2, and you see the 2 show up here in the definition of the function. And here we have our formal definition. I'll let you kind of read through that on your own, but I mean basically the point I want to point out here is that log base b of x is defined as the exponent to which the base must be raised to equal x. Really, a logarithm is just another way of writing an exponent problem. It's just another form, and we're going to see that on the next page. So if we turn over to the next page, alright, so logarithms and exponentials functions are really just two different ways of saying the same thing. They're inverse functions, they undo each other, but they say the exact same thing. They're just in different forms. In log form and exponential form, we do have things that are in common. For example, notice both exponential form and log form both have a base b. They both have that base b. Now in logarithmic form, the power is over here on the other side of the equal sign from the log. In exponential form, we know the power is what we raise our base to get our number. And then last of all, the argument of the log, this is what the n is what we're taking the log of. That goes to the other side of the equal sign in exponential form. Now what log basically says, notice that the log is equal to y and y is the power. So if we're taking the log of some number n, that tells us the power y, come over here to the other form, it tells us the power y that we have to raise our base b to get that number. And so that's the kind of thinking we're going to use when we're talking about logarithmic form. Let me say that one more time. If we have a base b, a log base b, then the log gives the power y that we have to raise the base to get our number. That's the number that we're taking the log of. And so sometimes it's easier to think of exponents in terms of log form, or also log form in terms of exponential form, in order to solve problems. Let's take a look at switching back and forth between the two forms. For example, we know that 2 raised to the third power equals 8. Well, what does that look like in log form? Well, remember, the base is 2, so the 2 goes down here. That's the subscript. And the power is on the other side of the equal sign. So so the question we're asking ourselves is 2 raised to what power equals 8? Well, obviously 2 raised to the third power equals 8. Come down here. We know that 3 squared equals 9. That means in log form 3 has to be raised to the second power to equal 9. See, it's the same numbers, they're just in different places. And then likewise, here we throw a fractional exponent here. We know that that just means square root, so this basically says the square root of 25 is 5. Well, in log form it looks like this. 25 is the base. The other side over here on the other side of the equal sign is our power that we have to raise 25 to get 5. So we can actually use this idea to help us evaluate logs and logarithmic functions. And again, it's that concept. What power of the base is equal to the argument? So let me just remind us of where these parts are. Remember, this is our base, and then the 16 is our argument. The argument is always the number that we're taking the log of. So this would read log base 4 of 16. So we have to ask ourselves, what power do we raise the base 4 to get our argument 16? Well, that's pretty easy. We know we raise 4 to the second power. Remember, the log gives us the power, and it has to be the second power that we raise 4 to get 16. So this is because 4 squared equals 16. Again, we have another one here. We have different base though. Now we have base 2, and we're asking ourselves, 2 raised to what power? We put an x in there. 2 raised to what power gives us 1 over 32. Well, here we have to put on our negative exponent hat, because we know when we have a 1 over, that's a negative exponent. And we know that 2 to the 5th power equals 32. So if we got 1 over 32, we know this needs to be a negative 5 power. So log base 2 of 1 over 32 has to equal what? It has to equal negative 5. Because, you write it in here, because 2 to the negative 5 power equals 1 over 32. This was our little side, I guess. Okay, so that's kind of how we evaluate logs or logarithmic functions. Now, there's a log that's used quite often. It's called the common log, and that's when we have a log base 10. And a lot of times we just write it without even writing it in. In other words, if I have log of x and I don't write the base in there, that means log of x base 10. We just, if it's not written, we assume that the base is 10. So in this first example, that means that this is base 10. Even though it's not explicitly written, we can assume that it is base 10. And so we're asking ourselves, 10 raised to what power is 100,000? This is an easy one, because 10 to powers, you just count the zeros. There's 1, 2, 3, 4, 5 zeros. So this is log of 1,000 is equal to what? There's 5 zeros, so it's got to be the 5th power is what we raised 10 to get 100,000. Now, nice thing about the common logarithm, because it is one of the more common ones, that's the name, we can calculate with a graphing calculator or any old calculator. So on the graphing calculator, you'll see a button over here next to the number pad that says log on it for log, and that is the common logarithm button. It's log base 10. So if I were to put in there log of 100,000, see, we get the 5 that we expected. And this first example is fairly easy to calculate, because obviously 100,000 is a nice whole number power of 10. But the next one, example B, there's not really a number that I can raise 10 to get 275. So here we actually have to use the graphing calculator to figure it out. And it's going to be some decimal that we're going to round to the nearest thousandth, like the directions say. So if I take 3 decimal places, round to the nearest thousandth, this is going to be 2.439. So this is about equal to 2.439. Another common logarithm is what we call the natural logarithm. And unlike the last logarithm, which was log base 10, this is log base e. And we already saw what e was. Remember, e was the 2.71, and the digits just keep going on and on and on. Remember that from the last section? Well, since e to some base is commonly used in different applications, it would make sense that we could have a inverse function for e to the x. The inverse function would be log base e of x, which is ln of x. Remember, I want to go back to that concept. The inverse function of an exponential function is a log function of the same base. So for the common logarithm, if the function is 10 to the x, then the inverse function is the common logarithm. And likewise here, if our function is e to the x, then the inverse function is log x. Those two functions undo each other. And again, here's our definition. When we have log base e, that is defined as ln x. And we just write ln x, it's shorthand for log base e. And so we could do things like evaluate the three examples here down below. We could take the ln, and we can use our calculator to help us with this. Notice right by the log button is the ln button. And one thing I also want to point out now is that the log button shares the place on the keyboard with the 10 to the x, which is its inverse function. And then the ln shares the same button as e to the x, because again they're inverse functions. So we could calculate the ln of 147, which is about 4.990 or 4.99. We could calculate ln of e to the fifth, which, let's do it with the calculator first, and then let's talk about why we get the answer that we do. So if I take ln and then hit second to get e, and raise e to the fifth power, and then close that parenthesis, and then also close the ln parenthesis, and press enter, notice that we get 5. And this should be expected. Let's go back to what we did at the top of the page. So this is equal to 5. Remember, the top of the page, the first example here, when we were evaluating logs, we were asking ourselves, well, what power do we raise the base to get our argument? Well, obviously 4 squared is 16, or 2 to the negative fifth power is 1 over 32. Or 10 to the fifth power is 100,000. Or, remember, what's the base here? This is base what? This is base e, right? Base e. E to the fifth power, remember the log gives the power, e to the fifth power gives us e to the fifth. Or e to the, example C here, e to the 3.7 power gives us e to the 3.7. Or here's an even better way to think about it. If e to the x, if e to the x and ln x are inverse functions of each other, remember they undo each other. So if e to the fifth makes a new output, then if I take the ln of that, it gives me back what I started with. If I put 5 into e and then put that into ln, I get back what we started with, 5. In other words, this is the generalization of what we just found. If I take the log of any base b of b to the r, I get r. In other words, if r is put into some exponential function, what do I get out? I get b to the r out. But if I put that into a log function, base b, then that's going to turn it back into r. That's why I see r goes in, and then r comes out. Because log and exponents are inverse functions as long as they have the same base. R in, r out. Okay, so sometimes this converting between the two forms, between the exponential form and the logarithmic form, can be useful when we're trying to solve equations. And so let's do a little bit of practicing rewriting between the forms. It's not real hard to do. For example, if I wanted to write this exponential form in logarithmic form, we know it's going to be a log. We know it has to have the same base. So this is obviously base what? This is base 3. So we know that our little subscript here is going to be a 3. And remember, the other side, the log always gives the power. And in this case, the power, or the exponent, is x. So the x has to go over there. And then the argument is 18. Or I could even go the other way. I could turn exponential, or I could turn log form back into exponential form. What's the base here? The base is 2, and the power is 6. So this tells me that 2 has to be raised to the 6th power in order to get x. And I can always do this. Anytime you have exponential form or log form, you can always switch to the other form. And you really, for this chapter, you just have to get used to being able to do that. So let's see how we can use this to help us actually solve a logarithmic equation. In this first example, we know that the base is 3 and the log gives the power. So in exponential form, this is 3 has to be raised to the 4th power to get the argument of x plus 3. 3 to the 4th power is 81. So 81 has to be equal to x plus 3, which very simply gives us the x that we're looking for. Gives us that x has to be equal to 78. X has to equal 78. Okay, so why don't you go ahead and pause the video, remembering that ln is log base e, and try to set up the next example, example B. See if you can write it in exponential form. Okay, so hopefully you got an idea of how to write this, and we're okay to change it to exponential form. The base is e, and it has to be raised to the 2nd power in order to get x minus 5. And then obviously I need to add 5 to both sides if I want to isolate the x. So it gives me that x is equal to basically e squared plus 5. And this we're going to have to calculate with a calculator, because e to the 5th is not that easy to calculate by hand. So we can just go e squared, close parentheses, and then add 5 to that. And let's keep the convention we've been using, round to 3 decimal places, so 12.389. So we have 12.389. So the last example here is go ahead and graph a logarithmic function, and I would contend that it's easier to think about this in terms of its exponential form. Remember that this is like in exponential form. This is 3, the base is 3 raised to the power of y has got to equal x. And so when I'm trying to graph this, my x and my y, why not write our y's first? Y's that we know. For example, I could do -2, -1, 0, 1, and 2 as my powers. Y is the power. We know that 3 to the -2, if we weigh, because y is the first example here, y is -2. If I take 3 to the -2 for x, I get 1/9. Or the next one, 3 to the -1 is 1/3. Or 3 to the 0 is 1. 3 to the first power is 3. 3 squared is 9. So we have these nice 5-ordered pairs, which should give us an idea of what the graph looks like, and it should be the same shape as the first one that we did on the first page. We have 1/3, -1, we have 1, 0, we have 3, 1, we have 9, 2. See how much easier it is to come up with the points if you put it into exponential form first and work kind of backwards? Because remember, the exponential and logarithmic forms are related to each other. So it's much easier to think about them in terms of exponential form in most cases. So we go ahead and put our points on. We got 1/9 is -2, 1/9, -2. We have 1/3, -1. We have 1, 0. We have 3, 1. We have 9, 2. And so this particular logarithmic function has the shape. Again, it's getting closer and closer to the y-axis, but never touching it. Remember what we call that line that it gets closer and closer to but never touches it? We call it a vertical asymptote, and in this case it's the line x equals 0. What's the domain of this in the range? Definitely doesn't cover all x's. It stops here at 0, and it doesn't actually equal 0. So we would use parentheses 0 to infinity, and then the range does cover everything. It goes from -infinity to positive infinity, because this graph goes down, continues to go down. We have a down arrow here, and then it more gradually continues to go up, but eventually it's going to cover all the y values. And lastly, we have a few applications here. So first one says the annual profit of a company in millions of dollars can be approximated by the function f of x equals 4.8 times the natural log of x plus 31.6, where x represents the number of years after 2000. And it says use this function to predict the company's profit in 2016. Well, 2016 is 16 years after 2000. So what does that tell us? That tells us that x is 16. So this is pretty simple. It's just a calculation. We want to find what f of 16 is, which is going to be 4.8 times the natural log of 16 plus 31.6. We're definitely going to need our calculator to come up with this answer. So we can take 4.8 times the natural log of 16, close parentheses, plus 31.6. Enter. So maybe 44.9. Remember, this was in the profit in millions of dollars. So this is 44.9. So we could say in 2016, the company's annual profit is expected to be 44.9 million. Okay, fairly easy. Another application, which is a more common application of the logarithm, is the Richter scale, which we all know is used to measure magnitudes of earthquakes. We've all heard that, especially growing up in Northern California and seeing some big earthquakes here. I can still remember going back to the one in 1989 that happened during the Giants and the A's World Series run. It says the Richter scale is given by R equals the log of I, where R is the magnitude of an earthquake on the Richter scale, whose shock wave is I times larger than the smallest measurable shock wave that is recorded by a seismograph. So it says, an example here, it says if an earthquake creates a shock wave that is how much times larger? It's 1600 times the smallest measurable shock wave capable of being recorded by a seismograph. It says find the magnitude of the earthquake on the Richter scale. All we do here is we say that R has got to be the log of 1600, because this 1600 is our intensity. It's our I. So we can calculate that. That's a common logarithm of 1600 is about a 3.2 on the Richter scale. So this is a 3.2. So we'd say the earthquake would have a magnitude of 3.2. Alright, that does it for this section 12.2. Thank you very much. Don't forget to do your self-check, and we'll see you in class.